So now that we can produce a signature, we've got to send the data that we actually signed and the signature over to the node, and we need a way to validate who this is coming from. That's the key here. Who is this? Validate. It's not enough to put in the transaction, it's from Bill. We have to validate that it is from Bill. And remember, we're extracting, you'll see, we need to extract kind of the public key out of the data in the signature to do this. So Ethereum here does something really cool to kind of validate the signature and who it came from. Before we do that, I did find the hexutil function again that I wanted to use here. So instead of just doing the big int, I can encode that, encode those bytes into the hexadecimal. And if I run make scratch again, now you can see it in hex, which is, it's more realistic. This is the way you would see it, say on an ether scan or something like that. Notice it says 1E. So again, 1D, 1E would be Arden, 1B, 1C would be Ethereum. If you go up on an ether scan and you see the VRS values, say in a detail, look at that V value, you'll see what that is. Sometimes they show the signature in the 65 bytes. Look at the last byte. Okay, so how is this next step really going to work? Well, let me draw this picture for you again here. Remember something. We have a decentralized environment. I keep making a point of that because it's decentralized. That means there's no place for you to register yourself. There's no username and password. There's no unique user ID. And so the system in a decentralized way needs to find, how do I give Bill a unique ID on the system as opposed to Jerry, as opposed to Eric, as opposed to anyone? And this is going to be done with that private key. So here's the idea. We each generate a private key. There's lots of ways you can do that. There's ways of doing it just like I'm doing it, just poof, randomly generate a private key. It can never be reproduced again. But if you lose it, it can't be reproduced again. So one idea is generate me a private key and write it to a key file. If you lose the key file, it'll never be produced again. So there are other algorithms that ask you for a mnemonic. Give me 12 or 24 words, and we'll use that to seed the private key generation. That way, if you lose your private key, if you lose your key file, you lose something, and you don't lose those 12 or 24 words, you can reproduce the same private key. You lose the private key, you lost all your money on the system. You gotta be able to not lose that. And so the mnemonic sort of system is really nice with that. Again, don't give up the mnemonics. You've given up your private key. And you might say, well, Bill, 12 words, I mean, can't somebody end up with the same 12 words? For somebody to pretty much choose the same 12 words in the same order would be like hitting the $10 billion lottery, okay? Like, it's not gonna happen. So we produce a private key. The private key for Bill is never going to be the same as the private key for Eric, let's say. So here's the private key for Bill. Here's the one for Eric. Now, how do we get a unique ID that can be a public ID? Well, that's the key. So what we do is we take the public key pair of the private key, and I forgot how many bytes of the public key we use, but we essentially take the public key and use that to generate an address, all right? We use that to generate an address. And that ends up being your public address on the system. That would be the same as if you registered on the system and you were given a unique ID in the database, all right? So this address, which is I produced from the public key, ends up representing you. So that's important. So anytime you generate a private key, the idea is, what is my address for that private key? We're going to use the public key to sort of generate it. I'm going to show you that now. So now how does this work? When we send this transaction over to the node, one of the things we're going to add is from address. I'm going to write into the transaction the address that it's from. And remember, we're going to attach a signature to this transaction. So here's the idea. On the node, I can take this data, and I can take this sig, and produce the public key. I can produce the public key that represents the data and the signature. Remember that this signature was produced by a private key. Then, with the public key, I can ask, what is the public address for that public key? And then I can do this final check. I can make sure that the from matches what we expect it to be off that. And this is going to be our check on the node. So every transaction that Bill sends, Bill better make sure that he has his address in there correctly. So when he signs it with the private key, and we go through this, that's always the same. That way, if Eric puts from Bill in here, puts my public address, which Eric knows, right? If Eric says, OK, fine, I'm going to say from Bill's address, but Eric can't sign the data with my private key. He can only sign it with his private key. So when this data goes to the node, we generate a public key. That generates an address. It's not going to be the same. It's impossible to be the same. Can't. Because the only way to make that work is by using the private key for that. I'm going to show you this. This is what we're going to be doing. And this is how we're going to get that final sort of verification. But the first thing we need to do is I need to show you how we can extract your public address from that public key. We got to kind of do that. So let's go back here. And I'm going to go back into our signature package now and do a couple things here. We have our signing. We have our signing, right? We have our verify signature. We'll get to that in a little bit. This is the function that I really want to focus on now. So given a value and a signature, what is your address? Essentially, what is your address here, OK? This function that comes from the crypto package does represent what your public address will be. So look, let me just take this for a second. Remember how we're generating a private key on the fly? OK. What if I take the private key, public key pair, right? I think I need to pass the address of it through. Oh, no, that's fine. And that's going to be the address. Watch this. And what I'm going to do here is fumpt. I think it's already in that format. If not, we'll fix it. OK. Let me just do this. And now what we're going to do is, given this private key that we're generating on the fly, go get the public key, and then let's figure out what our address is eventually on the blockchain. OK. So this, for that private key that we just generated and threw out, that's going to be my address on the blockchain. If anybody wants to send money to me related to this private key, they got to use that address. If I run it again, it's oh no, we're using the same private key. That's right, it's not changing. I forgot that, right? Remember, we hard-coded the private key up here. So for this private key, right, I'm always represented on this, in our case on the blockchain, as that being my public address. You want to send me money? Send it there, and my private key is always going to be represented by that address. How? Based on the public key. OK. But remember, the node doesn't have my public key. All it's going to get is some data and a signature. And so the key here is we need to extract the public key from the data and the signature. And it needs to match that number. So how do we just hack that in for a second? How do we hack that in? OK? How can we take the sign, and then also get back the same address, right? When all we have is the data that we signed and the signature itself. All right, that's what this function is going to do. So let's go back into our signature package here. And I'm going to add our from. So this is something we'll run on the node. So given some data and a signature, what is the address for that data and signature? Okay, so we're going to have to do things again here. We're going to take the data and we're going to stamp it, just like we did when we signed it. We're going to take the data and we're going to stamp it so it has our stamp inside. It follows our protocol. Now, in this case, the API that we're going to use wants to work in bytes. So what we're going to need here is our toSignatureBytes function. Now, this function is exported. I'm actually curious as to why, because it's been a while. So I'm going to do something that I like to do in my code bases when I'm trying to figure out who's using it. I just changed the name. And you can see that the database package here is using this. So that's why it became exported here. Now, the reason that got me confused is because it's below the line, right? And so one of the things I didn't do, if we're going to follow protocols here, is I'm going to put that above the line because it's part of the public API. Now, however, yeah, these are all functions. So there's no however. These are part of the public API, so I want them there. And then these are part of the unexported API, so we can have them there. All right, only export the things that are needed. But you see that little trick here? I just change it, change the identifier, see where it turns red, and I have an idea of where that's being used. Okay, so then I'm going to follow that same idea. I'm going to move it above the line. It's public, it's exported. And you can see what happens here now. The crypto package has the signature length. It should be 65, R32, S32, V1. And so I construct a slice of 65 bytes. And then what's kind of cool here is we can construct this R bytes of 32 bytes. And then the big package here, the big int, has this fill bytes function. You need to use this. And that way it fills everything in sort of correctly, okay? So we fill in the bytes, and we then take those bytes. So we're going to fill them in here, and then we copy them back into our signature. So what we're basically saying is we create a slice of 32 bytes of length, all set to a 0 value. We ask the big value to fill those 32 bytes in, and then we just copy them back into our slice here. 32 later, and then the last one. And here we subtract our Arden ID because we're going to use this in an algorithm that requires that to be 0 or 1. So we now convert our VRNS back into a slice of bytes, which is what we need. And now we can use this cool little function called crypto sig to pub. What this is going to do is take the data and the signature, and it's going to produce the public key for that data. Now, we don't know 100% if this is the right public key. You change the data, you're going to get a different value, right? And so we're going to have to do some checks later on to make sure, again, by comparing from fields. But look, this gives us the public key for that data. I'm going to show you this now in our Scratch program. And again, we run this independent of having a private key. So always think about this as being run on the node. So if we go back to our Scratch program, we can think that all that happened on the client. So what's going to happen on the node now? Okay, so at the end of the day, we want to run signature.fromAddress. Now, it needs the data. What it wants is that raw data, right? The raw data that we're using. So that's value. And then it wants the signature that we got back, and it wants it in the VRS format. Fine, VRS. Now that again is going to return an address and or an error. So let's do that. And that address already, so let's pretend that this is the address that we get on the node. If there's an error, we'll just return it. And then I can copy this. And what I'm going to do actually is move this down here so we can see it. So this is the address pretty much directly from the private key, right? I'm going to say directly because we're using the private key to get to the public key. And then this is the address that the node would produce based on the signature, right? So that's directly from the private key. This is really from the signature. Okay, put that little in there. And they better be the same. If they're not the same, we're in trouble. Like something's broken here. But this is the data we would send over the wire. This is the signature we would send over the wire. This isn't data that's stamped. We're gonna stamp it again ourselves on the node. But these two better be the same or we're in trouble. And they are the same. How cool is that? I mean, think about the math that's going on here with what's happening here. So what we're able to do on the node side is when we send this data and we send the signature, we're going to be able to produce a public key and extract the address. Now, we can't, I don't want to just blindly accept that address as gold, because what if somebody's trying to hack us and they're able to find a way of producing a signature, a data and a signature that produces a public key to do, like I don't want to do that. So we're going to have to make sure that when we send data, right? So the idea is this. When we actually build a transaction, I can't say from Bill. I want to say it's from this. And then what I want to be able to do somewhere in the node is say if address doesn't equal the node, right? Let's just call this the calculated address, right? Then, come on. Okay, return. Errors new. No match. And maybe we just do address, calc address, right? Just as a basic error. Now I need to do a fump.errorf got expected. And we're there. So, right, this is what we want. At the end of the day, we're going to have to do this check. We're going to have to send our address along with any transaction. So when we reproduce the essentially public key and the address that we believe this transaction came from, we can do a check, because watch what happens here. If I change even one value, right? I say, no, this is from me, some other address, right? I'm trying to hack the system here. Say, no, it's from me. I'm going to change this to like 5. Boom. Hey, no match, no match. Look, based on the data and the signature, because I changed the data, this is the new public key, right? This is a new address that we get. There's no way to validate that that was right or wrong in and of itself unless I'm able to compare that with something, and I want to compare it with the from. So this is going to give us that extra check here. So just in case somebody tries to send or alter some information over the wire, when we get it, we produce the from address, then we can use it to compare against the address that we expect to get that we've embedded in the data. Remember, this data is signed. So if somebody alters it, the signature is different, and that's why we're also seeing a different address. So as long as, if everything's kosher here, then the address and the from will always match the data and the signature that we get on the other side. And that gives us our security that Bill or Eric or someone did sign it with that address in mind, and we can go ahead and then process sort of that transaction. So I kind of love this. Let me also get this thing up. So git commit -am. We now have a from address support. There it is. I'm going to push it. This is cool. And now we have the ability on the node side to get the address that sent this based on the data and the signature. And as long as we put from in the transaction, then we can also validate that the person that is sending this transaction and signed it is who they are, because they've identified who they are here. And then when we calculate that from address from the signature and the data, we can compare it. And if it matches, beautiful. If not, yep, no good. So that's kind of part of the verification process that we can also do. But there's another verification that we'll want to do on the node as well.